This is video 821, and in this video our goal is to be able to solve three variable systems that are inconsistent or dependent. And we already talked a little bit about this in class and what this might look like, but we're kind of summarize it here so you can take some notes and make more sense of it. So here are some pictures, and these are all in your book, page 795. The inconsistent systems that we see here are systems that have an inconsistent solution set. So the first picture is of three parallel planes. Well, duh, they're never going to intersect. So the answer there is no solution. We have no common points of solution of intersection. The next one has one plane cutting through the other two. So what we have here is each plane, this yellow plane and this purple plane, have a different set of intersections with the gray plane. They're going to be described as a line. So the inconsistency there is there's no constant intersection in that case. And then finally, when we have three planes that intersect with three different lines, so instead of just two like we saw in the first one. So once again, all of these have inconsistent solutions. There might be some solutions that work for some of the equations, but there is no solution that works for all of them. The final set is the dependent. This is the one we already somewhat talked about in class. And this set is when the planes actually do intersect at a common spot, but the spot isn't just a point, it's a line. So we have a dependent system where it's dependent on one of the variables, x, y, or z. This one right here is, of course, where all three planes are the same. So those are going to always intersect everywhere. And what's going to happen there is the matrices will completely turn into all zeros. Everything will be zero. And that means that x, y, and z can be any triple that works for all three. So the examples we're going to look at kind of show us some different things. So here's a good summary. You can take a moment, pause the video, and read it over, but it's kind of already what I've talked about when we've seen in class and what I've just talked about just now. So read this at your leisure. This is also in your book on page somewhere in the beginning of the section for 8.2. So let's take a look at what the matrices will look like. If we have infinitely many solutions, we'll get that dependent systems case where that last equation says 0 equals 0. And we know that's always true. So that's why we have an infinitely many solutions. Another type we'll have infinitely many solutions is when we have two. Notice there was only two equations to start with here, 1, 2. This one will have infinitely many solutions if when I start to reduce it, nothing looks funky, like we have that 0 equals 2 case. We don't want that. If we have a 0 equals 0 case, we'll have infinitely many, but we know that from the fact that we'll have infinitely many in this case as well. These are only two planes, so of course two planes will never intersect at a single point. They'll intersect at a line. So you'll describe that line using these equations. And then there's the no solution. And this is the case where you'll get a contradiction in the bottom line. 0 never equals 6, so therefore there is never a single solution set that we can describe. There might be solutions between a pair of the different planes, but never between all three of the planes that we're talking about. So let's see this in action. So solve this system of equations using matrices, then check your work using your calculator. Now we've talked about in class how we're not going to use the matrix operations at this point anymore. It's good practice, so keep trying that using your calculator to check your answers. This is, we're simply going to enter into our calculator this matrix that we see here in augmented form. We'll let that be matrix A in our calculator. And then we'll perform the operation asking what is the reduced row echelon form of matrix A. So once we enter that into our calculator, it's going to give us the following result. So when we get a reduced row echelon form that looks like this, we see the contradiction in the bottom line that says 0 equals 1, which is never true. So we say that there's no solution to this system. And we can call the problem done. So let's take a look at another example. We're going to solve this system using matrices. We have only two planes that we're working with. We can still describe a solution set, And in this case, I'm not actually going to use my calculator. This will be a lot quicker if I just do it by hand. So here's my matrix, my augmented matrix. I'm going to do this quickly by hand because I know I only have one step to get at least 1 0. So I'm going to do row 1 plus double row 2, and I'm going to replace that with row 2. Put that where row 2 is. So let's see, if I double this, 2, 2, 6, 2, oh, this will be negative 2. And when I rewrite my solution out, my first row I'm just going to leave the same. 2, 1, negative 1, 4. And the bottom row will be the sum, so I'll get my 0, 3, 5, and 6. So I feel this might be easier to solve just by hand because of the fact that I can see now that there's going to be some decimals. There's only 2 equations, so it's only going to be 1 step. I'm going to get 1 0, and then I'm going to move on back into equation mode. And think of the bottom equation as 3y plus 5z equals 6. So this tells me that y and z are dependent of one another. So I'm going to solve for y and see what y will equal in terms of z. And it looks like I'm going to have y is going to be equal to negative 5/3 z plus 2. So my solution set to my system will be a system that's dependent on z, will work for any z, and the value for y is going to be negative 5/3 z plus 2. I'm also going to find x, but the way I'm going to find x is by plugging y back into the original equation. It's the first original equation. So I'm going to rewrite that in the equation form. And I'm going to plug in what I know for y that I see here. So I'm going to plug that in for y. So 2x will stay. Y is going to be negative 5/3 z plus 2 minus z equals 4. As I continue, I see that I'm going to change this z to common denominator with the other one. So now I can see that it's 2x plus negative 8/3 z plus 2, that's a 2 by the way, equals 4. Okay, so let's get x alone because I want to figure out what x is in terms of z. So it looks like I have 2x minus 8/3 z equals 2 after subtracting 2 from both sides. Add 8/3 z to both sides, and I get 2x equals negative, oh, it'll be positive now, negative 8/3 z plus 2. And one last step, dividing everything by 2, I'll get x will equal 4/3 z plus 1. So my x value for this system will be 4/3 z plus 1. So this is a dependent system. Here's how I would describe my solution set. This ordered triple will describe my solution set for these 2 planes. So when you have a pair of equations, you can find a solution set. It will be a description of a line in the 3-dimensional plane. So there's some good application questions. This is an interesting one when we're dealing with traffic control. So remember, our number 1 goal is to be able to analyze the situation and write multiple equations. So let's take a look at what this figure is. This is a figure describing traffic control, and if you're having a tough time seeing this, it is on page 798 in your book. This is a figure that shows the intersections of 4 one-way streets. So we notice that it describes how many cars are entering. So notice that this is a one-way going this way. This one-way goes the opposite way. And once again, this one's going to go to the right. This one will go to the left. So when it's saying 400 cars per hour right here, it's saying that's how many are entering that intersection. And then they might turn or continue going straight. So we don't really know. But when they exit this 4-way intersection, 4 different intersections, there's only 200 cars. So apparently a lot of them turn. And then here, 700 cars enter, 300 cars are exit, excuse me. 300 cars are entering on that side, and then 900 cars are exiting over here, and then 200 are exiting on that end. And of course, we have the descriptions at the bottom as well on how many are exiting and entering. This one's enter, and this one's the exit. So let's take a look at what this means. What we don't know is how many are going to be between here. So how many are in this little section here? And that's what we're calling X. This section is called W, Z, and Y. We don't know how many are going in between there. And that's our unknown, the number of cars passing between the intersections. So here's question A. If the traffic is to keep moving at each intersection, the number of cars entering per hour must equal the number of cars leaving per hour. That makes sense. Use this idea to set up a linear system of equations involving W, X, Y, and Z. Step B will be using Gaussian elimination, turning it into reduced row echelon form, to solve the system. And question C says, if construction on 27th Avenue limits Z to 50 cars per hour, how many cars per hour must pass between the other intersections to keep traffic flowing? So now Z has to be at most 50 cars per hour because of construction. So that's going to be one of our limitations that we'll see once we get through part B. We'll see what to do with C. So let's first set up that system by considering one intersection at a time. So let's consider intersection 1. Here's intersection 1. So intersection 1 is this one right here. It looks like from the north, 300 cars are entering that intersection. And from the west, over here, we have 700 cars entering that intersection. So altogether, there are 1,000 cars entering intersection I-1. Entering intersection 1. There are 1,000 cars total because of those two descriptions. But the question is, how many cars are leaving the intersection? Well, we don't know that because remember, we don't know how many cars are in this little section or how many cars are over here in this section where Z is. So we don't know the answer to that question, and that's actually what we're looking for. So we're going to describe intersection 1 as having 1,000 cars entering it, and that has to equal the number of cars leaving. Remember, that's the requirements to keep traffic moving. So that has to equal W plus C because what enters must exit. Let's do intersection 2. It's going to be identical in process, it's just going to be different numbers. So now we have a description on how many are leaving, because notice both of these arrows are leaving the intersection. So it looks like we have 900 plus 200, which is 1,100. That's how many cars are leaving the intersection. But how many are entering? Well, it's W plus X because of the diagram. So 1,100 has to equal W plus X. And we continue on this way. Intersection 3, which is down here at the bottom right. Once again, we can see that this says 400, and this says 300 cars entering, and then we have X and Y exiting the intersection. So 700 must equal X plus Y. And last but not least, our final intersection, intersection 4, down the bottom left corner, we see that there's 400 cars exiting down here, and on the left there's 200. So altogether that's 600 cars exiting. And I see that Z plus Y are the number of cars entering. So Z plus Y equals 600. Okay, so now let's set up our matrices, and we'll use our calculator to help us solve this quickly. So it looks like our variables are W, X, Y, and Z. So when I set up my matrix, I want to remember that. I need more space than that. Let's see here. So we have the first equation is W plus Z, so 1W plus 1Z. X and Y are 0, and we know that it adds to 1,000. And then W plus X, zeros for Y and Z, equals 1,100. That's intersection 2. Intersection 3, x plus y, w and z are zeros. That has to equal 700. And then finally, zeros for w and x, y and z add up to equal 600. These actually might be pretty easy to solve by hand because look at, we have a lot of zeros. We just have to do a few steps to kind of make it all zeros and ones. And of course we could do quick substitutions as well. Maybe some of you are like, why are we even doing matrices? Because these are really simple equations that we could substitute using what we know about x, y's, and z's. But let's just quickly enter this in our calculator. It looks like it's going to be a 4 by 5 matrix, and we'll see what we get once we use the reduced row echelon form. So it looks like when I enter this into my calculator for reduced row echelon form, it tells me, it gives me a matrix of 1, 0, 0, 0, 0, 1, 0, 0. It's telling me that it's going to be a dependent system. I see that bottom line saying that 0 equals 0, so I know it's a dependent system. And so now I'm going to transfer these back into equations and make my final conclusion. So let's take a look at what I have here. The bottom equation says y plus z equals 600. So that tells me that y is equal to 600 minus z. The middle equation will help me with x. That one says x minus z equals 100. So that tells me that x equals 100 plus z. And finally, w, the top row, describes w for me and says w plus z equals 1,000. So w equals 1,000 minus z. So let's take a look at what this means. That's my description of my solution set, of course, and of course z just equals z. But w, x, and y are all dependent on z. The question C is where we're actually going to now actually know z. Z has to only be 50 cars per hour because of construction. So that tells me that I can figure out what w, x, and y will be in that case. So let's take a look here. We have, if z was 50, that tells me that y would be 550. That's how many cars can be in that section. X would be 150. And w would be 950. So here's my solution to question C. After I wrote my system, I found out what the variables, how they're dependent on one another, and then how many cars can be in each section. Take a look back at the picture to kind of make sense of it all. Z is only 50, so that's going to be really tiny. That means W and Y will have to take the hit, so to speak. They're going to have to absorb more of those cars, which is why W and Y are so big. That's kind of an interesting way to kind of think about it. So let's take a look at your checkpoints. So give these your best shot. Definitely use your calculator to help you solve them. But these questions should be similar to what you've already been doing that you saw in this example, as well as what you've been seeing in class. So let me make this bigger for you. Here are your checkpoints. Bring your solutions into class.